came through it okay. But the longer you spend watching your kid in the NICU, the more children you watch die, unfortunately. We were in a NICU that had something like 100 beds in it, so there were all kinds of kids in and out of there. Some of them out healthy, some of them out not healthy. Not a fun thing. All right, so here we go. We're going to finish up here with chapter 23, inductance, RL circuits, and then RLC circuits. This is some important stuff, and this is the part where we don't have any homework assigned, and so I'm probably going to give you a couple of problems from these sections to work on, just because they're valuable and important stuff. But an inductor, oops, we need to turn on the screen here so you can see what we're talking about. Does that have a green light going on it?
This one right here?
Yeah.
Yeah.
So we've talked about the fact that if you have a current going through a magnetic, through a coil, through a wire of some kind, you can create a magnetic field. And if you have a changing magnetic field near a conductor, you can create a current. And this idea is this inductance thing. And so in electronics, we've designed these devices that are called inductors, where they're essentially just a coil of wire that you put a current through, and it creates a magnetic field when you put that current through it. But also the magnetic field, as it's changing, as it's being created by the current you put through it, actually induces a back current, that back EMF we talked about, in the coil that created the current. Right? So you have a current that's creating a magnetic field. The magnetic field that it's creating is inducing a back EMF in the coil that created the field. Self-inductance, we call this. You can also have mutual inductance, where one coil creates a current in another coil, and that's what they're talking about here. But the idea here is that you can use this. You can use this create a field, create a current, a back current idea to your advantage in electronics. In this particular case, they're going to use this one coil to create a current in the other coil, an induced current in the other coil, which will create another magnetic field, which will induce another back current in this coil, and so on and so forth. It's just a never-ending cycle. But when you have two coils, you have the EMF that is induced in the second coil is equal to the change in current from the first coil over the change in time in the first coil, times there's a factor in here. We're going to call this factor is going to be M, which is going to be the mutual inductance, which is going to have to do with the amount of coils and the closeness of the coil. I mean, it's going to essentially have to do with the physical characteristics of these coils. And then if you calculate the EMF that's induced in the other one, it's going to be due to the change in current of the second coil in time, and the same mutual inductance between them. And this mutual inductance is going to be measured for each individual coil, essentially, or in this case, these two coils. But it's going to be something that is that will be measured in any particular situation and then plugged into the equation as such. In some cases, mutual inductance will be a good thing. In some cases, it won't be a good thing. Some things you want to have that inductance, others you don't want to have that inductance. So here's some examples of where this is used. The heating element in a dryer, clothes dryer, is a coil of wire. However, what they do is, instead of just making a coil of wire that just goes one direction, what they do is they fold the wire in half and then they coil it. And so that the one coil going the one way has the opposite current of the coil that's going back. And what that does is it cancels out the inductance mostly. It reduces the mutual inductance because the magnetic fields created by those two coils cancel each other out. So you have one coil going with the current going one way, creating a magnetic field one direction down the center of this thing. The other one creating a magnetic field down the center of the other direction. So the mutual inductance almost cancels itself out so that you get very little warm-up time, essentially. So as the current drives through that mutual inductance and that back EMF doesn't slow down the heating up of the coil. And that's good because you want your heater to dry, you want your dryer to turn on quickly, as quickly as you can. You don't want a lot of things slowing down that current flowing through there. You also want it to cool down quickly. So for the same reason. So for a single coil, when you're not talking about two coils interacting with each other, you're just talking about with a coil interacting with itself. We have a self-inductance, which we call L, and again, it has to do with the physical parameters, the situation, the size of the coil, the length of the coil, the number of loops in the coil, and so on and so forth. All of these things are part of that self-inductance, and every inductive device, every electronic device really, has a self-inductance that can be measured. And the EMF that is going to be induced is going to be a function of that, a direct function of that self-inductance, and then the change in current over change in time. This self-inductance and mutual inductance have a unit. The unit is, we name it Henrys after, of course, a physicist who did all the discovering of this. The Henry is a ohm second. So ohms times seconds. It's also, you could also call it volt seconds per amps. It would also give you that same thing, but the units are in Henrys. And so so here's a nice little circuit, a very simplified circuit of how we can create a flash bulb. So flash bulbs usually require a lot of voltage, and one of the ways that you can create a lot of voltage is to switch back and forth between a battery and a capacitor with an inductor. The inductor is that little bumpy thing up top with the L underneath it. With an inductor in line with, or kind of in parallel with the capacitor. So you see those two arrow things, those are the switches, and they switch back and forth between the voltage source or the battery and the capacitor. And what that does is it slowly ramps up the energy between the capacitor and the inductor. The inductor stores the energy after time. The capacitor stores the energy immediately. So what it does is when you switch to it, the capacitor gets all that energy, and then when you switch off of it, that capacitor puts that energy into the inductor. And then when you switch back to it, you store more in the capacitor again, and then it puts it back in the inductor. And so it kind of switches back and forth between inductor and capacitor. But while you're doing this, you can store an incredible amount of energy in there. And so when you finally release that energy into a flash lamp, you've got several thousand volts sitting across this capacitor-inductor combination, and it can really punch a lot of current through that flash lamp. So you can see here that we now have two equations for this EMF. We have the inductance, change in current over time, and we have the number of coils, change in flux over time. So this is going to allow us to calculate what is going to be the value for the inductance. How are we going to calculate the inductance? The inductance, of course, can be directly related to the number of coils. So you have number of coils, and then change in flux over change in current. And of course, the change in flux is equal to a number of coils again times the cross-sectional area times change in current over the length of the inductor. We've seen that equation before. These are combinations of different equations from solenoids and other things, coils and everything. So when we bring it all down for a solenoid, which is the most common type of inductor, most inductors are just a solenoid, it looks like this. You have the permeability of free space, which is the 4 pi times 10 to the 7 or minus 7, whatever it is, that constant. Then n squared, which is the number of coils squared, number of loops squared, times the cross-sectional area of the solenoid divided by the length of the solenoid. So that is your mutual inductance for a solenoid. And since most inductors are solenoids or can be approximated by solenoids, that's a pretty good one. So if we want to calculate the self-inductance for a 10 centimeter long, 4 centimeter diameter solenoid with 200 coils, we need to convert, first of all, centimeters to meters, calculate an area, plug in the numbers, and crank it out. It's not that hard. You end up with 4 pi times 10 to the minus 7, which is your constant for mu naught, and the 200 squared, which is your number of loops, and then 1.26 times 10 to the minus 3 meters squared is what happens when you convert your centimeters to meters, multiply by 3, or square that, and multiply by 3.14 or pi to get your area. Remember, they had a 4 centimeter diameter, so they switched that to a radius by dividing by 2 first, 20 centimeter radius. And then you get a 0.632 millihenry, or 0.632 times 10 to the minus 3 henries inductance. And that's actually a fairly normal kind of inductance. It's a moderate inductance for a solenoid. Most solenoids are in the millihenry range. And guess what? You've all walked through a solenoid before at the airport or other buildings where they require you to, do they have these at the hospitals? Do they have security at the hospital? No? Some hospitals, they do have security. But essentially these little gates that you walk through, there are essentially 2 coils of wire, one on each side in the walls there. Big coils with lots of loops in them, and they've got a current going through them. So there's a magnetic field that is being created in between those 2 walls in that thing. And as you walk through it, if you have any metal on you, or anything that will conduct electricity, you're going to have an induced current in the metal as you walk through. It's going to do this changing magnetic field that you're going to walk through. It's going to induce a current in whatever metal that you have on your person. And that current that's induced in the metal is going to create a magnetic field in that metal. That magnetic field in that metal is going to change the magnetic field in the field that you walk through, which is going to change the current in those coils that you walk through. And that current change can be detected in the machine. And they'll know that you've got some metal. It's pretty simple. It's not a device that's difficult to create. We could create one in this room. In fact, we did in the lab yesterday. In the lab yesterday, you had a magnetic field, and you put a loop through it, and you noticed a current spike through the loop. It's pretty simple. The same would work if you put metal through it. In your case, you put a loop through it because it's easier to measure the current in a loop than it is in a flat piece of metal. But it would work either way. They actually know, they take into account things like fillings in your teeth and there are other metals in your body that can create a change in this, so they know what the average is for human beings with the normal amounts of metals in their system. We have iron in our system with nickel and potassium and calcium and all kinds of metals in our system. All these metals will create a change in that field, but if it's a big enough change, they know that that's not normal, and then they will check you for that. So it's not any kind of X-ray machine. It's not any kind of imaging machine. If you've watched movies before where it seems like it's an imaging machine because they can see an image of the person or something. Not that. It's not that at all. It never was. It never will be. It's much easier to detect metals using inductance than using some kind of imagery. The same is true with the baggage checking. They also check those using solenoid detectors, but they also have imaging devices involved with those, so they do both. So how much energy can be stored in an inductor? We mentioned earlier that you can use inductors to store energy. Well, how much energy is stored and how is it stored? In an inductor, the energy is stored in a magnetic field. When you put the current through the inductor and that current is flowing through the inductor now, you've created a magnetic field, and that magnetic field is a source of energy. It is a type of stored energy. It's like in a capacitor, you're storing energy in a capacitor in an electric field. In an inductor, you're storing energy in a magnetic field. The difference is that in a capacitor, when you're storing energy, there's no current flowing. You've just got charge built up on the plates. In an inductor, you can store energy while the current is flowing because the energy is stored in the magnetic field that is created while the current is flowing. So there is a difference there. Each one of them has different advantages. And in fact, when they're used together, like in the case of the flash bulb, they can use their advantages together to make even more advantage. So this is the equation. It's 1/2 Li squared. Again, that comes from some calculus that's not part of this course. And if we want to calculate how much energy is stored in a particular inductor, we have to know that self-inductance, L, and we have to know how much current is going through it. Just plug in the numbers and we're good to go. It's not that hard. This is where it starts to get hard. So if you remember, when we were talking about capacitive circuits with capacitors in them, we had this kind of build-up time where it took time for the capacitor to gain its charge. And then once it got to a certain charge, once it got to its maximum charge, the current stopped. With an inductor, it's a little bit different. With an inductor, the current starts off slowly and builds up to a maximum current. And once it builds up to its maximum current, it keeps it at that current. With the capacitor, what we measured is we measured the voltage, and you built up to a maximum voltage and it stayed at that maximum voltage. In this case, we're building up to a maximum current. So with a capacitor, the current flowed really fast at first, and then it petered off and slowed down as the capacitor charged. With an inductor, the current starts off really fast and then slows down. No, actually, sorry, it starts off really slow and then it speeds up to the maximum current and it stays at the maximum current. So it's exactly the opposite of the capacitor. With a voltage across an inductor, it's exactly the opposite as well with a capacitor. With a capacitor, the voltage starts at 0 and goes to maximum. And with an inductor, the voltage starts at maximum and then goes down to 0. So they're really weird things. A capacitor kind of behaves like a wire at first. Current goes to the capacitor at first. But then as the capacitor starts storing that charge up and it can't store anymore, it starts to behave more like a wall. And then it behaves like a cut circuit where current can't flow anymore because it's full. The capacitor is full. With an inductor, it's the exact opposite. As you start the current, the inductor says, wait a second, that's a change. That's a change in current. That's a change in magnetic field. And so it sends that back EMF to resist that change. So at the beginning, an inductor behaves like a wall for current, or it behaves like a cut circuit. But as it kind of gets used to that change, and that change is not so much of a change anymore after time, then it starts to allow the current to go through. The back EMF releases that current, essentially. The back EMF goes down, and that current begins to flow until it gets to a maximum. And then at its maximum current, there is no voltage across it. There is no resistance, quote unquote. There is no back EMF to it. And so it just allows the current to flow normally like it would through a wire. So they're just the opposites of each other. And because of that, the functions are going to be the opposite. The voltage function for a capacitor looked like this. And the current function for a capacitor looked like this. In this case, it's going to be the current one that looks like this. The current, for turning on, is going to look like this, where the current is going to ramp up slowly and then go to a maximum instead of the voltage ramping up slowly and going to a maximum. But it's still going to have a time constant, but the time constant is going to look different too. The time constant for a capacitor looked like the capacitance times the resistance. Is that right? Or 1 over, well, anyway, it looked different than this. I think it was 1 over capacitance times resistance, whatever it was. But for an inductor, it's the inductance divided by the resistance. So it looks different for an inductor. For turning off a capacitor or an inductor, when the inductor has current going through it, and then you turn off the current supply, it actually has the opposite effect. it looks kind of like turning on for a capacitor. And it slowly, when you first turn it off, it immediately starts to turn off, and then it slowly dies off later. So it turns off very quickly and then slowly decays. So, and this time constant is the same thing. It's essentially 60% of the time for it to do these things, for it to ramp up or die down. So that for this particular capacitor resistor combination, where you have 7.5 millihenries with a 3 ohm resistor, you're going to get a 2.5 millisecond time constant. So this combination, it allows for 2.5 seconds approximately for it to get to 60% of its current when you turn it on, and about 2.5 seconds to get down from 60% of its maximum current. It's actually 67 or something like that, percent of its maximum current when it's turning off. So when it's turning off, it declines to 0.368 of its initial value. When it's turning on, it increases to 0.632 of its total value, whatever it is. And every time constant, it will drop another 0.368 or climb another 0.632, whatever it is. But it's just the opposite of capacitance. So it's not something we haven't seen before. All right. So I think that I'm going to assign you a homework assignment from here, just one problem. I like this one right here. This one that has the A on it. What is the characteristic time constant of a 25 millihenry inductor has a resistance of 4 ohms? If it's connected to a 12 volt battery, what's the current after 12.5 milliseconds? So this is going to be a problem. I'll actually put it into the homework here really quick so that it's actually in there. Let's add a new question. Let's log in. Write out your solution in detail and return it to the teacher. Okay. So this is what it's going to look like. You're not going to actually submit anything with this. Question type essay. Let's see. Let's do a file upload actually. Do a file upload question. So then you'll essentially take a picture of your work. You can take a picture of your work if you need to, or you can turn it in by hand. So you can also upload a picture of your work to the teacher. All right, so that one is now add question to assessment. There we go. Save settings. So now that should be in the assessment here. Chapter 24. I don't want to put that in. Are we in chapter 24 or 23? Dang it, that's not what I wanted to do. Let's try this again. 23, chapter 23, here we go. Questions, the assessment settings. Oh, it won't let me add one to this one. Okay, you'll just have to do it by hand. Anyway.
You should just publicly message.
Let's go to the assessment here, chapter 23. We'll just put it in the settings. Assessment has been taking, modifying some settings will be a problem, but modifying other settings won't be. Here are some questions that you need to turn in handwritten. One. Oops. One. There we go. Now we're doing good. All right. So that will be one that we'll do. We're running out of time here. We got to get going. Okay. So now, what happens if we have these things all in a circuit together? What really happens is kind of interesting. Because the inductor, when you put a current through an inductor, there's a delay because it stops the current at first and then it lets it through. The voltage coming at the inductor and the current coming at the inductor and the current going through the inductor are out of phase. So you start your current with your battery and then it hits the inductor and the current slows down, and that doesn't happen until later. So if you have a changing current, if you have an AC current, you have a current driver that's going up and down in voltage and up and down in current, and then an inductor that has a voltage that's changing and a current that's changing in a different phase. So the waves are not lined up with each other. If you look at the currents and the voltages, they don't line up. The voltage across the inductor and the current across the inductor are not, at peaks together. They're actually, when one's at a peak, the other one's at zero. And when the other one's at a peak, the other one's at zero. So it's not like a resistor. Remember, resistors, when the voltage is high across a resistor, the current is high across the resistor. But with an inductor, when the voltage is high across an inductor, the current is zero through an inductor. And with a capacitor, it's also different. Remember, when the voltage is high on a capacitor, the current is zero. Right? And so every one of these behaves differently. And so when you put them all in a circuit together, you get this weird interchange. When the capacitor has a high voltage, the inductor has no voltage. Right? When the inductor has a high voltage across it, the capacitor has no voltage across it. And the resistor is different than both of them. Right? And so this seems weird. It seems like it would be really confusing, and it is. But the beautiful thing is that if you can get it just right, if you can tune it just right, and make your capacitor just the right size, and your inductor just the right size, you will get them working in tandem so that they are getting a maximum amount of energy into the circuit at the same time. So you have to balance it. And when you're balancing it, what you're doing is you're actually creating a balance of frequencies. You're actually balancing these waves. To do this, you have to understand that each one of these oppose the current in some way. A resistor, of course, opposes the current just by being a resistor. The inductor opposes the current by having that back EMF when you start up the current. And a capacitor opposes the current by filling up with charge, right? So each one of them has this ability to oppose the current, and this ability we call the reactance. Each one of them has a different reactance. For an inductor, the reactance is 2 times pi times the frequency of the current. So this is for AC circuits. So it's going to have some frequency going through it. 2 times pi times the frequency of the current times the self-inductance of the inductor. So that's what we call the inductive reactance. The inductive reactance of a resistor, can you guess what it is? It's just the resistance. And then the capacitive reactance, right here, is 1 over 2 times pi times the frequency times the capacitance. So it's just very similar to the reactance, the inductive reactance, but it's 1 over 2 pi fc instead of just 2 pi fc. And then, of course, for resistor, it's just the resistance. If you want to know the total reactance from resistor, capacitor, and inductor combined, we call that the impedance of a circuit. And it actually kind of behaves, it kind of looks like, the, oh, actually they don't do that in this section, they do that in the next section. So anyway, so if you're going to calculate these things, you just have to know the frequency of the circuit, the frequency of the driving current or the driving voltage. And so at different frequencies, you'll get different reactances. For example, if you increase the frequency for an inductor, it increases the reactance. So the faster that the current is changing, the more the inductor pushes back. Well, that makes sense because inductors behave, they don't like it when there's change. Remember that magnetic fields, when they're changing, cause more inductance. So they react back more. So more change means more reactance, more pushback from the inductor. With a capacitor, it's the exact opposite. More change, it's a 1 over the frequency thing. If the frequency changes more, the capacitor behaves more and more like it's not even there. It reacts less and less because it gets filled up less. If you're changing that current, going back and forth more and more, it doesn't have time to build up on the capacitor, so the capacitor never builds up enough charge to push back. So capacitors and inductors behave exactly the opposite, but if you can get that frequency just right for the size of inductor and capacitor you have, you can fill them both up. You can have energy storing up to the maximum possibility in both of them at the same time. And that's what we're going to try to do in this last section, where we talk about the RLC circuit. So RLC, when you put a resistor, an inductor, and a capacitor in series with a AC source, then you can put just the right frequency through to get the maximum amount of energy out. In fact, what you're really going to do is you're going to store a maximum amount of energy in here as that current goes back and forth and back and forth. However, we do need to know some things, and one of the things we need to know is what is that overall reactance of the circuit? What is the overall resistance of the circuit? And it turns out that it kind of looks like, what does that look like? The square root of some things added together squared.
It looks like
It looks like the Pythagorean theorem, and it is actually the Pythagorean theorem. It's the Pythagorean theorem in what we call phase space or phasor space, where each one of these things, because it has a frequency, is like a vector that's rotating in a complex plane. And those rotating vectors at some particular place create a triangle, and to calculate the third side of that triangle, you need to use this Pythagorean theorem. Here they kind of explain it, showing how the currents and the voltages change with respect to each other. And if you can get it just right, you can get the current and the voltages to peak at the same time across the inductors and the capacitors, and you can get a maximum amount of energy in the circuit. In this example, they just calculate that total reactance, which we call the impedance. Z is the impedance. So you have to have the resistance squared, and then you have to calculate both the inductive reactance and the capacitive reactance, take their difference, and then square it. It doesn't really matter which one you take the difference with first, because you're going to square it in the end anyway. But you take the difference there squared, add it to that resistance squared, take the square root, and it comes out in ohms. And it is frequency dependent. So for this particular resistance, capacitive, inductance combination, you get 190 ohms of impedance at 10 kilohertz. If you change it to a different frequency, it will change. Has a different impedance at different frequencies. And so if you calculate all of them at different frequencies, you'll find that you get a minimum that impedance goes down to a minimum point at some particular frequency. And that's what you want. You want this circuit to have almost no resistance, or the lowest resistance possible at some particular frequency. And when does that happen? That happens when the inductive capacitance, or the inductive reactance, and the capacitive reactance are equal. When they're equal, this thing becomes 0. And then your current can become a maximum because this number down here becomes as small as possible. It just becomes R. It just becomes Ohm's law. And when that happens, you can solve for the frequency where that happens, and we call that the resonant frequency, F0. And it's 1 over 2 times pi times the square root of the inductance times the capacitance. So this tells us the resonant frequency for any RLC circuit in series. It actually tells us the resonant frequency for an RLC circuit in parallel as well, turns out. But this is the resonant frequency. This is what makes your cell phone work. Okay? Your cell phone has an RLC circuit in it with an adjustable capacitor. It probably has an adjustable capacitor and adjustable inductor. But it can adjust that L and that C to a particular frequency. And the particular frequency that's going to adjust to is the frequency that your phone is communicating at. It's not exactly this simple because cell phones actually use many different frequencies and they kind of jump around on them. But it's still basically this idea. And so what it does is it creates a circuit that resonates with this particular frequency. And then it looks for that frequency out there in the gazillions of frequencies that are around us every day. And it finds this tiny little frequency, this tiny little wave that is barely even noticeable out there. But because your phone is tuned to that particular frequency, that tiny little wave builds up in this circuit a huge current. It gets captured by the antenna, and this circuit builds it up from a tiny little thing to a big thing because it resonates inside of there. It bounces around back and forth, and it builds and it builds and builds till you can hear the voice of the person you're talking to. Now, cell phones are digital phones these days, so the frequency, the signal coming over is digital, but the idea is still the same. That digital frequency needs to be amplified because it's too small, it's too tiny for you to use it when it comes through the air at first. And so knowing that resonant frequency is extremely important. So if you want to calculate that resonant frequency, you need to know the inductance and the capacitance. Easy. Those are things that are written on the component that you're putting into electronics. You just write those numbers in here, put it into the equation, calculate it for this particular inductance capacitance combination. You have a resonant frequency of 1.3 kilohertz, which that's kind of like that's a AM radio station. So for an AM radio station, if you want to tune into that AM radio station, you're going to need a circuit that has that kind of inductance and that kind of capacitance in series with some kind of resistor, connected to an antenna, and you will be able to pick up that signal. It really is kind of that simple. You can also use Ohm's law. You're going to use Ohm's law with the RMS because it is, the root mean square, because it is an AC signal. You can use that to calculate the amount of current in that situation too. If you have 120 volts and 40 ohms of resistance, or 40 ohms of impedance, you can actually calculate how much current you're going to get out. The power is going to be different, however. The power is going to be different because those waves are not in sync all the time. Right now, they're lined up just right to store the energy at a maximum amount, but still the waves are not on top of each other, not in sync, they're not in phase. So you have to use this cosine of a phi thing, this cosine of phi, which tells you how much these things are out of phase with the voltage source. And that cosine of phi is equal to the resistance over the impedance. So if you calculate the resistance of your resistor divided by the total impedance of the circuit, you're going to get a number at a particular frequency. And so, because the Z is calculated at a particular frequency. So you calculate that, and then your power is equal to I times R times the cosine of phi. So, I times V times the cosine of phi. And that will be your power, your average power in any RLC circuit. And that takes us to the end of the end. Oh, we need to have a homework problem from there. Did we do a reactance calculation? Let's do a reactance calculation problem. Let's see. All right, so let's do this one here. And let's do, it's a capacitor. Let's do an inductor. Oh, they don't, the numbers didn't come through here, did they? What is the characteristic time constant? The resistance. What? It has a characters time constant. I don't remember what it was. We'll call it 50 ohms. Okay. The current flows 6 years from here is connected to a let's call it a 50 microfarad capacitor. Ooh. And then if a 10 kilo ohm, oops. A 10 kilo ohm. What volume inductance should be used? Let's see, go back here. 20 kilo ohm reactance. That's good. 10 kilo ohm. Okay. Then let's go to next section and do one more problem. Let's calculate a resonant frequency, a power factor. An RLC circuit consists of 40 ohm, 58 finite impedance. An RLC.
Dad,
But
I have a question for Mother.
yes,
When do you teach your next class?
right after this one at 11. Fine. What is it for? Okay, so copy this. Okay. 25 resistor. 25 resistor. A 100 milliamp. Inductor and an 80 microfarad capacitor. If the voltage source has 5.6. Okay, that will be good enough. So let me save that. That shouldn't change anything for you. Open up chapter 23, and in the instructions you have 4 extra questions.
Are we only doing 1 attempt on all of them?
On these ones?
All of them.
I don't know, does it say 1 attempt?
Yeah. It's normally like 7.
That's not good. Let's fix that here.
I don't like that.
23.
Right? I got the math right on the first one. I just missed one of the multiple choice ones. I was like, oh god. This is gonna be bad.
Let's see. Failed attempts 7. And then we go to 23 questions. Source settings. That one's going to have to change. Okay, so it should be good now. Yep. All right. Are you going home?
Yeah.
Do you need this printed off to work?
No.
between like 10 and 1 anytime.
I teach at 11 tomorrow
Till when?
till noon,
Mm.
and that's it.
I'll be here at some point tomorrow.
Okay.
I'm gonna try to work on the homework a little bit tonight so that
All right. Sounds good.
if I come in at like, will you be here earlier than 11?
Yeah, I'll be here at 8.
Okay. So I might come in around 9 or 10. We'll see how much sleep I get.
Okay.
Might be here around 9, might come here around 8. But the first problem is, so that's promising.
Oh, that's not a good one.
Although, so for the EMF equation, it said it was like EMF is V times L times V. So I had the velocity and I had V that was given, but it said the length of the cylinder that you're moving around was like 0.11 meters or something. But in the book it says that L is the distance between like the two rails that you're moving it through. But when I multiplied all those, like just the length of the cylinder, it was correct. Is that how it's supposed to be?
I'm not sure which. I'd have to look at it.
Okay, no worries. I was curious.
I'd have to look at your work.
Okay. See you tomorrow.
Yep. You guys can go ahead and get started on your experiments again.
Experiment.
What's that?
Experiment.
Your activities.
You matter because if I just get it out, you're imaging. No.
I forgot to end my class recording, so I got to do that.